All right, so our next sort of section that we're going to be learning is the chemistry that has to do with biology. So we've looked at what our living organisms are. We've looked at kind of some general science, scientific method, theories versus hypotheses. Now we're going to look at what chemistry you need to really understand the rest of the biology that we're going to do this year. And so we're going to start with water. And water is a very unique molecule, and we're going to talk about why it's so unique. But because it's so unique, it's really what's responsible for life on Earth, which is why when we look at other, when we try to look at other planets, we're always talking about water. That's why water, does it have water? Could it sustain water? Why is water so important? So that's what we're going to look at. And what we're going to look at tonight is kind of the chemistry of water. Because water really is a unique molecule, and it has to do with its chemical makeup. So that's what we're going to look at. So first we need to go back to physical science and remind ourselves on the difference between covalent bonding and ionic bonding. And that's going to come up a lot this year. So if you don't remember these from last year, please make sure you spend some time on them, because I'm going to start referring to covalent bonds, or I'll say these are bonding ionically, and I'm going to assume you know what I'm talking about. So covalent bonding is when atoms share electrons to fill their outer shell, and we call that outer shell the valence shell. And so you maybe drew atomic diagrams where you draw almost like bullseye diagrams and you'd put the electrons on. That's a real boiled down version of the atomic model. It's called the Bohr model. In fact, when you get to general chemistry in high school, and we will talk later this year about when I recommend you take general chemistry, you're going to learn something called atomic orbitals, which is a much more accurate depiction of where the electrons are, but it's harder to draw, which is why we fall back on that kind of bullseye or Bohr model so often. And if you remember, that outermost ring is called the valence shell. And atoms want, in general, 8 valence electrons. And they don't always have 8. Actually, most of them don't have 8. And so they have to do things like bond or transfer electrons to get their 8. One exception, which is especially important to these notes, is hydrogen. Hydrogen only wants 2 valence electrons. It's really small. 8 would be too many. 8 would be a crowd. So covalent bonding, the atoms share their electrons. So like if I have a sandwich and you don't have one, and we each want a sandwich, we can share one sandwich between us, and then we both have a sandwich. So that's what covalent bonding is. It's sharing those electrons. And I'll show you some concrete examples of that in a minute, because that's what water does. So water is covalently bonded. Carbon dioxide is covalently bonded. Stomach acid, which is hydrochloric acid, is covalently bonded. And then you can contrast that to ionic bonding, which is where atoms transfer electrons between them and then become charged. So like if one atom has some extra electrons, it might give those electrons away to another atom that needs them. If atoms gain electrons, remember are negative, so if they gain electrons, then those atoms become negative. If atoms lose electrons because they're losing negatives, they become positive. Positive and negative charges attract, and you get what's called an ionic bond, which incidentally, is much stronger than a covalent bond. Ionic bonds are stronger than covalent bonds. So you have things like table salt, NaCl, sodium chloride, baking soda, sodium bicarbonate, NaHCO3. Just as an aside, there's actually a third type of bonding called metallic bonding, but unless you go into a field that deals specifically with things like metal alloys, you're really not going to deal with that even in a general chem course. Alright, so if water covalently bonds, then let's take a look at that. It's 2 hydrogen atoms and 1 oxygen atom. And you can see here, and let me get my pen, oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Oxygen actually has 8 electrons total, but 2 of them are a lot closer to oxygen's core. So they're not valence electrons. They're not the ones doing the bonding. Outermost valence electrons do the bonding. That's why we care about them so much. That's why we name them. There's patterns of valence electrons on the periodic table so that you can know in an instant how many valence electrons something has. Hydrogen has one valence electron. One and one. Hydrogen actually only has one electron total. So notice oxygen needs two more. 1, 2. And each hydrogen needs one more. So if oxygen and hydrogen share these two and these two, you get something that looks kind of like this, where oxygen has its original 6, and this is why I color-coded them, plus the 2 from hydrogen. 6 plus 2 is 8, exactly what oxygen wants. Each hydrogen then picks up one electron from oxygen, and so they have 2. And remember I said earlier, atoms want 8 valence electrons, except for hydrogen, which wants 2. And so we can draw it this way. This is called a space-filling model. Or we can draw it this way, where we just kind of draw little lines. And so in class often I'm going to draw it this way because it's easier and why bother. And you'll notice that water has this kind of bent shape. Okay, that is not true of all molecules of its size. So if you look at something like carbon dioxide, we have the carbon, and carbon actually has what's called a double bond, which is a little stronger than oxygen's single covalent bonds. So there's one oxygen, and here's the other oxygen. And carbon dioxide is what is called linear. It's in a line, whereas water is bent. It's bent. And again, in a general chem class, you would get into why oxygen is bent, but carbon dioxide is linear. And you'd be able to figure that out, and your teacher may give you a molecule and then you'd have to say what the shape is and things like that. And I'm happy to go into that in depth with anybody kind of one-on-one, or if there's a couple of you who really want to delve into that, I'm happy to explain it in more depth. But it's enough to remember on its surface that water is bent, and that creates some very unique properties for water. Quickly, the shape has to do with these extra electrons here, and if you remember, electrons are negative and negatives repel other negatives. So these electrons here and these electrons here are repelling these electrons here and here. So instead of getting to have this nice linear shape, these extra electrons kind of push the hydrogens down and you get a bent shape. And again, I can go into more detail and we can talk about bond angle and stuff with anybody who's interested in that, but for the scope of biology, just remember water is bent. So because water is bent, it is also polar. So this is one of those words that we had on the first day, and a lot of people said, I don't know what word that is, I've just lost my mouse. Here it is. So water is polar. And what that means is the oxygen attracts the electrons more strongly than the hydrogen. So again, it's like if we're sharing a sandwich, but I eat more of it, we still shared the sandwich, we still had some sandwich, but I get more. So oxygen attracts electrons more strongly. And remember, electrons are negative, so the oxygen side ends up with a negative charge. The hydrogen sides, because they're having electrons pulled from them, end up with a positive charge because they're missing some negatives. And once again, if you want to get into why that happens, it has to do with something called electronegativity, which is how strongly atoms pull electrons to themselves. And oxygen has a higher electronegativity than hydrogen. And if you want to get into why oxygen has a higher electronegativity, again, that's something you can ask in class. That is something, again, you'll learn in general chemistry. It's good enough now to know oxygen kind of pulls the electrons to it, so it ends up with a negative charge, and understanding why that's negative, and that hydrogen ends up with a positive charge. Anything more than that, feel free to ask. So, actually, let me go back for a second. This is because water is bent. So if we look again at carbon dioxide really quickly, carbon dioxide is non-polar. It doesn't have a positive and a negative side. And that's because it's linear, or it at least has to do with the fact that it's linear. Some linear molecules are polar. Some bent ones are not polar. But in this case, the fact that it's bent is causes water to be polar. The fact that carbon dioxide is linear causes it to be nonpolar. Molecules, and when we say molecule, we're talking about atoms that bond covalently. Something like salt is not a molecule because it bonds ionically. Molecules are either polar or nonpolar. And there's a spectrum. Something could be weakly polar, but generally we speak about polar or nonpolar. And again, if you want to know why, like how we determine that, let me know. But oils are nonpolar, which is why oils don't dissolve in water. It's why they don't mix, because, and this will be in the next set of notes, we like to say like dissolves like. In other words, if something's polar, it dissolves polar things. If something's nonpolar, it dissolves nonpolar things. Most alcohols are basically nonpolar. So interestingly enough, things that don't dissolve in water, because water's polar, may dissolve in alcohols because alcohols are basically nonpolar. But that's also why the oil and the water don't mix, because one is polar and one is nonpolar. And then what's really exciting is what soap is. And so we'll talk about soap in our next set of notes. Now, because water is polar, it actually experiences forces of attraction between water molecules. So this is the negative side again. This side is positive, as is this side here. But then this side here is positive. So anytime you have more than one water molecule, and think about in a drop of water, you're going to have millions of water molecules, they're going to kind of orient themselves so that their positive sides are attracting to the negative side of a different molecule. And that force of attraction between them is called a hydrogen bond. Now, up here, this says it's not a true bond. Okay, true bonds are ionic bonds and covalent bonds, and they are way more, their force is so much stronger. So for example, a hydrogen bond is only 5% as strong as a covalent bond, and a covalent bond is weaker than an ionic bond. So hydrogen bonds are not bonds, which is why if you boil water, it turns to steam, you get individual water molecules. So in steam, you'll get like one water molecule, but it's still the hydrogen bonded to the oxygen. You haven't actually broken that bond. What you've done is you've overcome this force of the hydrogen bond. Now, that said, there are many different intermolecular forces. I'm going to write that word out. It's going to take me a while because I'm writing with a mouse. But inter, meaning between, like intramural, molecular, so between molecules, intermolecular forces. And there are many different intermolecular forces. You'll learn about 3 or 4 of them. Well, which is about 3 or 4 of them in general chem. And of all the intermolecular forces, hydrogen bonds are one of the strongest of the intermolecular forces. So even though it's not even remotely as strong as a bond, if you compare it to other intermolecular forces, it's one of the stronger ones. And that fact that hydrogen is bent, therefore it is polar, therefore it experiences hydrogen bonds, is what makes it such a unique molecule. And tomorrow in class, we're going to do some activities that have to do with water and have to do with some of its unique properties. And then we'll follow up with some notes on how those unique properties affect life on Earth. So please feel free to add any questions you have to the comments in YouTube, although notice that I do delete comments that have nothing to do with what we're talking about. Or you can ask in class. Have a good night.